So first of all, I'm Andrea Crotti. I'm Italian, as you might understand from my accent, but I work in London for a web company. And here is a slide. This is my Twitter account, and there's a link for the slides, which are generated with RST, and the code is all available there. There are tests and so on and so forth. All the code is done for Python 3. It's easy to port to Python 2. I will show you also in one slide what are the differences. As a preamble, the reason I did also this talk is because I finally want to clarify in my mind what's the difference between all these concepts. And maybe now I finally got it. But if I say something wrong, please correct me. So we're going to talk about what is a generator, what is an iterable, an iterator, what's the difference between them, and how to use them, how to define them, and actually why do I care, why do I even use them. And this image is very nice because that was my brain, how my brain was before when I was thinking about these things. I knew how to use them, but I still was not entirely sure what they actually meant and how they were defined. So the problem we are going to solve is embarrassingly simple, but I think it's clear enough to show in a presentation. We just want to generate a list of possibly infinite even numbers, basically. So we have a function which tells you if a number is even or not, and then we first start with the simple list comprehension way of generating a list of even numbers. We take a range, start and end. We check that the range is valid, and then we return with a list comprehension the list of even numbers in that range. Very simple. So why this is not fine? Well, it's fine. There are two problems. The first problem is that we generate the whole list in memory and then return it. And the second problem is that I can't reuse this logic. I want to be able to do other things. For example, how do I get the first 10 even numbers? Well, I can't really do it in the other approach because if I am passing the end, I don't know how many in theory. Well, I know in practice because it's a very simple problem. But suppose it's something more complicated like prime numbers. I don't know what would be the range to see how many there are. So what I have to do, basically, is to have to rewrite the logic in another time, which is very annoying. So I do this loop, and then until I don't have 10 numbers, I generate a new one, I put it in the list, and I return it. So that's clearly quite bad. So, but it would be nice instead to do something like this. I would like to have a function which is called gen_even, which I don't have defined yet, but I will soon, which just generates me an infinite stream, and I don't have to pass a start at the end. And here I have two versions of the same thing. So this is itertools islice, which takes an iterator, and then it takes only the first 10 elements where I pass here. And this is the same thing. This is exactly what this does. So you call this gen_even, and then you loop over, and then you yield the next 10 times. So so the question is, how do I define this thing? First line is how you define something like this in Haskell, because I think it's very nice. It was my first love in programming languages, in a way. And all you have to do is to say x for x in a range from x 0 to infinite, and then this is the guard, which says the modulo of x and 2 is 0. Very simple. Well, in Python, it's not that different, really. So here we have a generator expression, and we use itertools count to go from 0 to potentially infinite again. And this is generate all the numbers. And then the guard is also defined in the same way, more or less. And this is a generator expression. So this doesn't create a list in memory, but it only generates something on demand. And this is exactly equivalent to this thing here. So I start from 0, or from, depending on what I pass, I check what is the next even number. And then while true, so I loop over to potentially infinity until my RAM can contain the number. and then I just yield the number every time. So let's give some definitions, which is this was kind of the hardest part of the talk, because I changed the definitions probably 10 times each, because I found hundreds of different, and they're all somehow similar but different. So I just tried to find a way to make it clear. So this is a generator expression. It's something that evaluates to a generator, and is defined like this, simply with brackets. The same thing as the list comprehension, except that you have the round brackets instead of the other one. A generator is the same thing as a function, really. The only difference is that in the function somewhere there is a yield. So this is a bit, I think, a bit the confusing part, because it uses also def to define it, but it behaves in a way completely different. So there have been some discussions in the PEP about generators to create a new keyword to say this is a generator. No? But in the end, they just decided to call it in the same way, and so that's how it is. So what is an iterator? Instead, iterator is something that tells you how you iterate over something. And to do that, it defines the __ next, which is just next in Python 2. And this is the simplest possible example, which if you loop over, and I'm going to show you some live coding now very quickly. So if you loop over, this is also some example. This is just a list. This is a set. And you can also iterate over these things. And an iterable is something that tells you if you can iterate over something. And has to define the __ iter. So these two things normally are defined together. So you normally don't see it really like split in this way. That's also why I think it's a bit confusing to define them separately. But that's what the real difference is. I'll just show you live 1 second. If I now, probably you can't see much. Let me see. Should I change the colors?
It's okay.
No? So simple iterator, yeah. I do this, and then I do next s. This will do 42 forever. Instead, if I do simple iterable, and I call iter, well, this returns me the list iterator. If I do list of this, it returns me the list 42. So this doing a list, or I can also do just list of this actually. Sorry. Yeah. So if I do a list of an iterator, I actually it constructs the list out of it, like expanding it. So if it's an infinite thing, it will of course continue forever. All right. So let's go back to the thing which we were trying to define. So this is the actual generator, defined as a generator expression and as a generator. And I can show you how that it works. That's very simple. But so generator, then even I can say start equal 3. Well, I assign it to something. And then here, if I look here, there are a few things. So the thing which we want to know is just next now. But then I'll try to explain what this method also mean. If I do next g, I get 4, which is the next even. Do next g again, next g again. Yeah. If I do now close, it means that I stop. I stop it. So if I do g again, next g again, it will raise a stop iteration. Okay. And now let's see the same thing defined as an iterable. So this is slightly more convoluted, but it does exactly the same thing, because here I have an object instead, which I initialize with the number, and then I define the iter and the next. So as you can see here, the iter is just returning the object itself. So it basically says, I am iterable, and the way to iterate myself is found in the next method, which is defined in myself. So that's what actually this means, really. So and the next simply gets the next even, and then increments the number, and then returns it. So in a way, this is a bit more clear than the generator, because here it's clear that whenever you use this thing and you call next, there is some state that is saved somewhere, and now it's saved in the object. So the difference with this is that in this state is maintained by the Python interpreter somewhere in memory, and it keeps track that even the last time you call it was 2, while here is more explicit that so that's basically the difference. So to know when you have to write a generator or an iterable, so generators are simple to write. You don't have to have this boilerplate of the init and so on and so forth, because the generator, they keep track of the context for you. But sometimes it's more useful to write a full class, because you can have extra methods, you can have more complex state handling, and so on and so forth. So as a general suggestion, just use generator unless you need something really a bit more complicated. There are some things, however, that you should be aware of when you use generators too much, maybe. And one is that in some particular cases, you might have a condition where something fails only after a certain amount of computation, right? This is a very silly example, very artificial, but I couldn't find anything. But I know I've been bitten by this a few times, so it does happen. So but what happens here is that I loop over until 101, and then I create a list with in a standard way, so to say. And when I reach 100, there is an exception, right? So what happens if I do the same thing with the generator? Well, they both work, they both fail, except that the generator will fail only if you actually reach that point. But you don't have to reach that point all the time. I can show you just now as an example. So now I have generators, what was called overflow list. I just call it, and it fails. And now instead I use the generative the way, so I say of gen. Now nothing happened, right? So I do next, still nothing. It works fine, but nothing happens. But if I do now this, and now I finally get my, oh no, I got the stop iteration. What did I do wrong? Ah no, ovgen, sorry, that's the wrong one. Yeah, okay, yeah, I got the error. So that's one thing to keep in mind. So, yeah.
What was the problem there? So
I was using the wrong variable here.
No, you mean buggy code
Ah.
ahead. So what's the bug here?
Well, the bug is that there is assume that this is not like an exception that you want to raise, and you're not catching anywhere. It's just, no, I mean, this is just something that happens after a certain time, and if you do it, if you do this computation all ahead, you see the problem immediately. If you do it with the generator, you might not see it until you actually get all the 100 values. Because in a way, what I'm saying is that the generator is better, because in that scenario, it means that you are using less memory, maybe you're doing less computation, but it can hide these kind of things, which you shouldn't have anyway, but that's one thing that can happen. No. Another thing which you can do with this yield statement is to have coroutines. A coroutine basically is just as a generator, except that the yield is used to assign something to a variable. So instead of producing values, it consumes values. This, I think, is a very nice example because this is a function called grep, which takes an initial pattern, and then it will stop the execution until here, until you actually send some input to this coroutine, and then it will continue the execution until again it reaches this point, and it will consume your input this way. This is the same thing. Well, I'm going to show you now how it works. But this is the same thing. The only thing I've added is this result, which I use to basically get some feedback from what this coroutine did, to have some kind of output, which is not just printing out to the standard output, which is now very interesting. Is that clear? I will show you now. So we go now. I have grep, and then I pass line, right? Well, and I create a generator. And now I send something to the generator, and I say, let me see if I don't remember how to call it. Pattern in line, yes. So this, for example, line. I'm checking if the pattern line is contained in this one that I'm passing. Can send line value to adjust. Yes, I have to do next G the first time. Yes, forgot. Yeah, and now we reach the yield, and now I can send the line, and it says I found the pattern. Now I do it again with something that is not found, and it tells me it is not found. So basically, this is there waiting for me forever, and they're sending some new input and doing something with it, which is very cool. The same thing I can do with the result. I also have to generate a simple result object, which is just a class with only the value found or not found. And then I do this, and then do the result line R. Okay. And now I do again the same thing. I do the next G the first time. Okay, now it's saying found pattern line, but also now the difference is that this R which I passed now is R found is true, so it got modified because the object which I passed now is still linked to the original object, and I can have a side effect on the thing which I passed in the coroutine. Now, if I do the same thing and something which doesn't match again, it says it's not found, and then I check again, R found, and now it's false. So, very nice. Let's see how much stuff. Okay. Just a few differences between Python 2 and Python 3 for the code in the slide. Itertools filter is just filter now, because filter also general thing. X-range is gone, and this is renamed to range. Previously, you had to define next, and now you have to define underscore next. And also, next was a method on the object, and now is a built-in. And also, the last thing is that yield from has been added. I haven't shown anything about that, but these are mainly, I think, all the differences relative to this particular area from Python 2 and Python 3. An example of how these generators, coroutine things are used, for example, is a monocall, which is a library similar to all the libraries we've seen today, async.io, and I think this is a bit slightly older. But yes, here the cool thing is that you can write some code that looks like it's synchronous, but in the end is asynchronous, and using just this Python magic of coroutine and generator. Here there are some resources, and I also have some extra slides, which I don't know if I have time to see or not. I'll just show you this about the for loop, maybe, because maybe it's interesting. What the for loop does, basically, in Python, is that it takes something, it calls next on it, and then it checks if there is a stop iteration. When it gets a stop iteration, then it stops. And another interesting thing is that you can define an iterable in another way, defining get item. If you define get item, it means that it will check, you pass an index, for example. I think there is an error actually. Item should be indexed. Okay. So you can, what happens when you do a for on a list is similar to what you can do with this gen iterable get item. Because it will try to call get item on the object on index 0, index 1, index 2, until it gets an index error. And that is not what is done in the list. But you can define something that behaves like a list, just defining this thing. And you don't need to have next and previous. And yeah. So this is not very used anymore, but it's still perfectly valid both in Python 2 and Python 3. And then as very last thing, there is like slightly bigger example of how to use generators. And this is a Sivo Eratosthenes, this is in Haskell. How it works is that you remove from the list of next numbers all the ones that are multiple of a prime which you already found. So I see 2, basically, and then I say, OK, all the numbers which are multiple of 2 now can be removed from the possible primes. Then I see 3, and then I can remove 6, 9. Then I say 5, and then I remove 10, and so on and so forth. So this is the definition in Haskell. And in Python is slightly longer, but it's also quite nice. So yeah. So here I pass an initial iter count 2, all the numbers from 2 onwards. And then here I say next of these numbers. And then I redefine them, excluding the multiples of the prime which I already found after I yield it. So, yeah. OK. All right, so here there are some resources. My slides are already there again. And I think that's all. Time for questions, if you want. Any questions?
Can you yield from nested functions? Like you have a function and you yield there, and that's the generator then. But can you call a function in there and then yield from there back to the top? Do you understand what I'm saying?
That's not the yield from though.
Yeah, you can do with the yield from, but you can do the same even without the yield from. You just have to. So the way you can re-yield something is just you do a loop and then for this in this, and then yield. I don't know if it's clear. I think I do it.
Thinking that now you can make a generator with one function. But
Yeah.
maybe you can make a generator with an entire piece of your program and more complex.
Yeah, of course you can. You can do all sorts of crazy things. Yeah, but if you overdo it, then it's probably hard to understand what is going on.
Yeah, of course.
That's the point. Yeah.
Another question?
Thank you.
Okay.